to recap a little bit each time what we've done. So we have proved that if F is a piecewise affine map, if F is a full branch piecewise affine, then this implies that the Lebesgue measure is invariant and ergodic. Notice that this holds also if you have an infinite number of branches. Okay, our whole proof worked absolutely fine even if you have an infinite number of branches. So what I've been doing now is just getting a little bit used to some interesting consequences of this. Okay, and then we will generalize this and we will relax this piecewise affine property and look at some more general results. But first, if you remember using Birkhoff's ergodic theorem, we have the uniform distribution with respect to Lebesgue, right? And we had this discussion about normal numbers. You remember? Yes? So that's one interesting immediate corollary of this in number theory. It's a nice application of this result to number theory. Today what I want to do is study a little bit more the structure of ergodic invariant measures. And I want to make first of all this observation that if you have two dynamical systems, so suppose we have a dynamical system F next to X, and suppose you have a dynamical system G from 1 to I. And suppose that this is a metric space, these two are metric spaces, so we have the Borel sigma algebra here. And suppose we have a map H, which is a measurable map. So suppose H is measurable. You know what measurable means? Measurable map? That the preimages of measurable sets are measurable. Okay? So if you have a measurable map and you have a measure here, suppose we have a nu is a probability measure. I'm sorry, just one second. Let me just press it. So if you have a measure here, suppose this is a probability measure. Sorry, you have one here. I'm sorry. You have a probability measure here. Okay, then you can use this map H to define to what's called push forward this measure, and we can define a probability measure mu here, defined in this way. So let H star, so let mu of A. So we want to define a probability measure here. So we take a set A here, and we define the measure mu of this set by the pre-image of A. So here we take H minus 1 of A. Right? So we define the measure of A to be equal to the nu measure of H minus 1 of A. So all we need here is that we have a measurable map between these spaces, and we can push forward the measure from one space to define a measure. It's like you take, instinctively, you take this measure and you map it onto this space so that the measure of the set A is how much measure you put into it. Yeah? In other words, you look at the measure that is in H minus 1 of A, and this means these are all the points that map to A. So whatever the measure of this is the measure that you define to be of the set A. Okay? So we define a new measure mu. So this defines defines a map which we call H star. It's called a push forward from M of X to M of Y. Okay, where this is the space of all probability measures. Space of all probability measures on X or Y. X or Y. Okay, and this measure is defined by H star of no. Okay, is by definition of some set A, is by definition no of H minus 1A. Okay, so this is our new measure mu, is the push forward by H of the measure no. Okay? So, the reason why we're interested in this is we're particularly interested in the case in which now, so this doesn't actually use F and G for the moment. These are just two spaces with probability measures. Now, a natural setting in which we have these kind of maps is when F and G are conjugate. Right? This is what we spent a long time talking about in the first part of the course. So there is a relation between the dynamics, and in the first part of the course we discussed about what topological properties this conjugacy preserves. Remember, if it's a topological conjugacy, it preserves certain topological properties, right? But if it's only a measurable conjugacy, in other words, it's only a measurable bijection here, then it preserves certain properties of these measures in the following sense. So if recall that H from X to Y is a conjugacy between F and G, okay, if what is the property here? If H composed with F, so you apply F and then you apply H, so H composed with F is equal to G composed with H. This is the conjugacy, right? So you take a point here, you apply F, and then you apply H, and that's the same thing as applying H and applying G, you get to the same point. Okay, we studied this a lot. So, the lemma that I will leave as an exercise is that if F and G are, it is sufficient for them to be measurably, for this measurably conjugate. So I did not talk about measurable conjugacy, but it's kind of in between a simple conjugacy. If you remember, I emphasized that a priori all you need is H to be a bijection. Then you have a stronger situation where H is a homeomorphism, okay? A measurable bijection is something not as strong as a homeomorphism, but a little bit more than just being a bijection, okay? If it's a homomorphism, then of course it's also a measurable bijection. If you take the Borel sigma, if H is a homomorphism, then it's also measurable with respect to the Borel sigma algebra. So if F and G are measurably conjugate, then, so we have two properties. Wait, let me write it. And we have, so, H star mu is, so H star mu lives here, right? Remember, these two measures live in different places, right? Let me use H star nu because that's the notation I used before. So H star nu, so nu lives here. So nu is a measure inside the space X. H star nu is a space inside the space Y. Okay, so maybe I should write this measurably conjugate by some conjugacy H of X, Y. Okay, and nu is a probability measure on the space X. Then H star nu is G invariant if and only if nu is F invariant. In other words, if you now have the dynamical system and nu is not just any probability measure, but it is an invariant probability measure, and H is a conjugacy, which means it connects the dynamics, then the mu that you get as H star of nu is also invariant with respect to G. Okay, it's fairly expected, but it's an interesting observation. And also H star nu is ergodic if and only if nu is ergodic. So I'm going to leave this proof as an exercise. It's also in the notes, but it's a relatively simple exercise. But so what this means is that H star restricts to a well-defined map on the space of invariant ergodic measures, right? So then H star is well-defined on the space. I'm not sure if I introduced this here before, but we can write E of X to E of Y. These are the ergodic invariant measures. Okay, ergodic invariant measures. So if you take an ergodic invariant measure here, then it maps to an ergodic invariant measure here. So we're going to use this as a tool to construct new ergodic invariant measures, right? If we know that we have an ergodic invariant measure here, we can use this to construct ergodic invariant measure here, because this is the name of the game, right? We have developed a tool, which is Birkhoff's ergodic theorem, that tells you that if you have an ergodic invariant measure, you have a whole bunch of very powerful conclusions, and now we're looking for ergodic invariant measures. Okay? So far we have seen examples of Dirac delta measures on fixed points of periodic orbits. Those are ergodic invariant measures. And we've seen Lebesgue measure in this particular case. Okay? So today I'm going to use this push forward idea to construct two more examples, or in some sense to illustrate how we can use this to see that there are more ergodic invariant measures in various situations. Any questions about this? Okay. Okay, so the first example is a fairly simple one.
So, if we don't know, there's two maps conjugated, and both are invariant, ergodic. So, the conjugation is related also with the measure. The measure the other side is obtained by a push forward, or it's not necessary?
Not always. This is what we're going to see today. I'm going to show you two, in some sense, extreme opposite examples. In both cases, we're going to construct some measures using the push forward, but in one case, it's going to be kind of what you expect. In another case, it's going to be not what you expect. Let's see these two situations. So let me write example one here. Is the following. Let's look at the map. Consider the map F from -2, 2 to -2, 2. Which is this? It's a quadratic map. F of x equals x squared minus 2. So x squared, you know, from high school, middle school, what this looks like. This is just a parabola. So this is -2, 2. So this is just the parabola like this, right? This f of x equals x squared minus 2. So notice that this is not on the unit interval, but essentially it's a full branch map, right? In the sense that we have two intervals, each of which gets mapped to the whole space, right? We have minus 2, 2 gets mapped to all of minus 2, 2. This is minus 2, this is 2 and minus 2, and this one is also mapped to everything. But it is not piecewise affine. Okay? And it's not even expanding. I anticipated to you that, or even when we did the topological conjugacy, we see that for some of the things, all you need is that it's expanding. Here it's not even expanding because we have derivative 0 here. Okay? So certainly it's not clear that Lebesgue measure is invariant here. And we're going to find an interesting invariant measure that is equivalent to Lebesgue measure. Yeah? And the way we're going to do it is by comparing it to this other map, which is just, so here this map is from 0, 1 to 0, 1, and it is just the 10th map. Okay, so we can, if we want, we can write it as tz equals 2z and 2 minus 2z, depending on whether z is in 0, 1/2 or z is in 1/2, 1. Okay, this is the explicit formula. So this one we know something about, right? Why? This is a full branch, piecewise affine. You agree? It's all piecewise affine. So Lebesgue measure is invariant and ergodic for this map. Okay? So Lebesgue measure. So here Lebesgue is invariant and ergodic. Okay, now it turns out that these two maps are conjugate. And the way we show that they're conjugate, fortunately for you, we do not need to do any complicated construction because they're conjugate by a formula, okay, by a very explicit formula. So we take the map H, it actually goes in this direction, and the map H is given explicitly by H of Z equals 2 cosine pi Z. So you can see that the domain and the range are right? When Z is equal to 0, then cosine of 0 is 1. So this maps to 2. So 0 maps to 2. And when Z is equal to 1, this is cosine of pi, which is minus 1. So this maps to minus 2. Okay, so this is a map from 0, 1 to minus 2, 2. Okay, it flips it, and it flips it is natural that it should flip it because it needs to send this point to this point, so it flips 0, 1 onto here, okay, and I will leave it as an exercise to check that this is a conjugacy, right? So H exercise H is a conjugacy. So you just plug it into the formulas, okay? To see that it's a conjugate, you literally just plug it into the formulas. We have the formula for F, we have the formula for H, we have the formula for T, so you just check that the formulas, that H composed with F is equal to T composed with H. Okay? Is it a topological conjugacy? Yes, it's in fact much more than a topological conjugacy. This is differentiable. Its inverse is differentiable. except at the endpoints, because it's 0, right? So this is this h, so let's just sketch here. So h goes from 0, 1 to minus 2, 2. So 0, 1 to minus 2, 2, and it goes something like, so 0 we said goes to 2, if I'm not mistaken it goes something like this. Is that right? Because yes, because it's just 2 cosine pi z, so when z is 0 this is 2, it's just a cosine curve. Okay? So it's not exactly diffeomorphism, because at the end point it's not a diffeomorphism on the closed interval 0, 1, because the derivative here is 0. And you remember if the derivative is 0, it means the inverse would have infinite derivative, so the inverse is not differentiable at the endpoints. Okay? But it's a diffeomorphism on the open interval, so it's almost a C1 conjugacy. So it's a very strong form of conjugacy. Okay? This is really remarkable, and in some sense, this example is almost unique. Okay? In fact, this, for some of you who might ever have heard of Chebyshev polynomials, I don't know if you've heard of it, it's a special class of polynomials. This is an example, the simplest example of a Chebyshev polynomial that have this kind of property that they are conjugate in some sense to versions of tent maps. There's a kind of very special class of maps of this kind. Okay? So this is a conjugacy which is more than measurable, is more than topological. It is essentially C1 conjugacy. Okay? And this is going to help us a lot in determining the properties of this measure here. Right? So H is a C1 differential on the open interval 0, 1, right? To the open interval minus 2, 2. Okay, so now we would like to define, so let mu definition is H star of Lebesgue. Okay, so here we have Lebesgue measure. The reason we choose Lebesgue measure is because we know that Lebesgue measure is invariant and ergodic here because we've proved it. And now we define a measure here, okay, that is just a push forward of Lebesgue measure. And by the exercise that we did before, mu is ergodic and invariant. But it will not be Lebesgue measure here, because Lebesgue measure is not invariant and ergodic. So we want to find out what measure this is. So mu is this, and mu is ergodic and invariant. So there's a few calculations to do which I'm going to leave as an exercise because it makes much more sense for you to do them. But let me just explain now how we do the calculation. So the calculation is simple. It is just so what's the definition of mu? So let A be an interval in 0, 1. So we want to know the measure here. So we take an interval here, A, B, right? And we want to know what the measure of this interval is. Okay? So the measure of this interval is the pre-image of this. So we have, this is an interval in minus 2, 2. And then we define H star, so H star, so mu of A equals H star of Lebesgue of A, which is equal to Lebesgue, which is equal to Lebesgue of H minus 1 of A. Okay, this is all just by definition so far, right? The definition of mu of A is the H star of Lebesgue, and the definition of H star of Lebesgue is Lebesgue of H minus 1 of A. So we look at this interval here, and this will have some pre-image here. Right? This will be H minus 1 okay? And so all we need to do to determine the measure of this by mu is to determine the Lebesgue measure of its pre-image. That's the definition of the push forward.
I'm sorry, I don't see what's the relation of F and G? How do they approach those?
They're conjugate by H.
Yeah, but when we look at the measure, we just forget about.
No, not at all. Not at all. So, first of all, it's important. These are conjugate.
Yes.
Okay, remember what conjugacy means. So there is a H is a bijection. In this case, it's a C1 diffeomorphism that connects the dynamics of these two. Okay. Now, independently of that, just the fact that we have this map allows us to define measures here by pushing forward, for example, Lebesgue measure here or any other measure. Okay. So given Lebesgue measure here, we can define another measure by this formula here. We can define a new measure mu. Okay, this is a new measure, so I'm defining it like this. Okay, I'm defining it as h star, which by definition is the Lebesgue measure of h minus 1 over a. So I take any measurable set here, I look at its pre-image under h, and I look at the Lebesgue measure of this, and I decide that I call the measure of the set A to be the Lebesgue measure of its pre-image. This is just a definition of the measure mu. Then we stated a lemma that said now these two measures, if there's a dynamics and if H is a conjugacy between the dynamics, then in fact whatever measure we construct here will be invariant and ergodic. If we're using an invariant and ergodic measure here to push forward, then the measure we constructed here will be connected to the dynamics in the sense that it's invariant and ergodic. That's the key point. Right? So the measure that we construct is invariant and ergodic. So mu is invariant and ergodic. Okay, then, so maybe I should write it then. Mu is ergodic and invariant. I can see puzzled faces, but I'm not exactly sure what you're puzzled by. So, is that okay so far? Yes? Okay. Remember, it's enough to do intervals, right? I said at some point, I think I mentioned, because of the Kolmogorov extension theorem, basically there's a little technicalities to be really strict, formalize this, but essentially, if we understand what the measure of any interval is, then we know what the measure is overall, okay? So we only really need to describe a measure on intervals, okay? So how do we know, if we take an interval here, how do we know what the Lebesgue measure of its pre-image is? Yes, it's very different. It's just by H, right? So in fact, I deleted the graph, but I had a graph here, right, which was like this, right? This is the map H. This is the map H. So now I have, this is 0, 1. This is minus 2. 2. So I take a set here, A, okay, and I look at the pre-image of the set in 0, 1. This is H minus 1, right? This is A, and this here is H minus 1 of A. You agree with that? Yeah? H is a bijection, so it's just got one component, the pre-image, and we just want to measure the size of this, the Lebesgue measure of this. And that's what we're going to assign. So every set that we have in A, we take the pre-image and we look at the Lebesgue measure, and that is going to be our definition of mu of A. So it's a little bit like taking Lebesgue measure on 0, 1 and spreading it out in a way that is according to this map, right? So when this is very small, you're concentrating a lot of measure here, right? Because if you take a little interval of size epsilon with Lebesgue measure epsilon, then here this will map to a very small interval here, which will still have measure epsilon by the new measure, right? Whereas here you have the same interval of size epsilon, it maps to something big, but this will still have measure epsilon, right? So you're distributing the mass in a way that is no longer uniform. That's what's not Lebesgue measure. So this mass will be, there will be more mass here and here than there will be in the middle. Okay, this measure is distributed, and we can calculate exactly the density of this measure. Yes?
But the length of the interval is 1, or the length of the image is 4. So how, this is 1 and the image is 4.
Yes, we are spreading it out over an interval of size 4. You've got your 1 kilogram of mass, right? And you just spread it out along the interval. You still have a probability measure, right? Because the pre-image of everything here will be everything here. So if you apply this to the set A, which is your whole interval minus 2, 2, right? Then you will get the Lebesgue measure of h minus 1 of minus 2, 2, which is the interval 0, 1, which has probability 1. Right? So because of this push forward, you always get a probability measure, whatever your space is.
So it's not of length 4, it's of length 1.
No, length is not a measure, right? Length is the length of the interval.
That's the Lebesgue length.
Well, that is the metric, let's say.
This is a
Don't
silent measure.
Sorry?
Silent measure.
No. This is not a sign measure. So there's a little bit of confusion between the length and the Lebesgue measure, right? So, yes, so Lebesgue measure coincides with length on intervals, right? But, yes, okay. So Lebesgue measure here on 0, 1 is the length of this interval 0, 1. Okay, but now we're using this to construct a new measure on a new space. And the space could be all of R, could be the interval, it could be whatever, another space. Okay, and so we're taking this 1 kilogram of mass. You need to think of measure not so much as length or distance, but as mass, right? As 1 kilogram of sand that you are spreading out in your space however you want. Okay, so you're taking this 1 kilogram of mass here and you're spreading it out in the interval minus 2, 2. And you're spreading it out in a way that depends exactly on this function, because you can see this is telling you exactly how much mass you're giving to every place. Right? If you take this and you look at its pre-image, then this amount of mass, here you have 1 kilogram of sand, here you're taking, it's uniformly distributed in 0, 1. So if you take this of length epsilon, it's an epsilon amount of mass, and you're taking that epsilon and you're spreading it out exactly here, right? If I take another epsilon of the same size, but I take it here, then I'm spreading it out in a much smaller space, in a very small interval here, okay? So the new measure, mu, if you measure according to this mu, this interval here, it will have measure epsilon, and this will also have measure epsilon.
Yeah. For example, if you take h minus, h is C1 diffuse, and so h minus is differentiable. So if we take integral of h minus derivative is silent measure of Lebesgue measure. Like h minus derivative is the Lebesgue measure is integral over a is equal to our measure. Is a silent measure, and Radon-Nikodym theorem, it's just marginal for our measure. Like if one set A is a Lebesgue measure is 0, in this case mu also 0. If Lebesgue measure is 1, so complement of this set is 0, so complement of this set is 0.
Yes, the reason I objected to sign measures, because usually you think of sign measures when they're measures that may have negative mass. It's just a measure. It's just a measure. You call it sign measure, but it's just a measure. That's what a measure is, right? So it's just a measure that is given exactly by the formula you said. So this I'm going to leave again. So we can use so we can write, as you said, we can write the measure. Let me get this straight here. So the length. So mu of A, which is equal to Lebesgue measure of h minus 1 of A, okay, as you said, is equal to the integral between a and b, right, of the inverse of the derivative of the absolute value of the inverse of the derivative of the inverse. Dx. Okay, this is just how you calculate by the fundamental theorem of calculus, basically. Okay, so this is the inverse because what you're doing is when you look at the inverse, you're taking this and you want to know how big the image is, right? Because how big the image is exactly the measure of A, right? So you want to know how big the image is, so you just take this interval and you integrate the derivative along this interval and you get exactly that. Okay? So I will let you check that this, so exercise, that this is exactly equal to 2 over pi times the integral from a to b of 1 over square root of 4 minus x squared dx. This is a formula. That just comes from this, and you're doing some manipulation, some trigonometric identities, and so on, and you get this. Okay, it's in the notes anyway. Okay,
But
so
this is the value is always positive.
yes.
So what's the relation to sign measures?
No, that's why I think it's confusing. I understand why you're calling it sign measure because you're thinking as a general theory of sign measures. Forget about sign measures. This is just a measure. Okay? It's just a measure. You define the measure. This is a measure where the size of the measure of each set is given, the measure of any interval is given by this integral. Okay? Because this integral gives you exactly, because this integral is the integral of the derivative of h minus 1, right? So it's telling you exactly the size of the pre-image of A, and therefore the Lebesgue measure of the image of A. That's exactly what it's giving you. So this here is called the density of the measure, right? So, in other words, so 2 over pi 1 over square root of 4 minus x squared is called the density, is the density, or the Radon-Nikodym derivative, as you said. Did you do this in the course this year, or had you just done it before? You did it in the analysis course. Okay, perfect. So the Radon-Nikodym derivative of mu with respect to m. Radon-Nikodym derivative, the mu by the m. Okay, so it's the density with respect to Lebesgue measure, because here you've got Lebesgue measure here, and so this density is something like, so this is the density on the interval minus 2, 2. All right. Minus 2, 2. This is 0. So this density is, let's see, when x is 0, this is 1 over pi, right? So when x is 0, this is square root of 4, which is 1 over 2, 1 over pi. So 1 over pi is about 1/3, so it's somewhere here, okay? And then as x tends to plus or minus 2, this goes to infinity, this density, right? So this looks something like it's not really. So what this formula means, what this density means, as you know, is that when you if you take any interval or any set here, A, right, then the measure of that set is given by the area under the graph here, right? That's what this integral means. So this 2 over pi is a kind of normalizing factor and makes it so this is integrable, this function. So in fact, the area under the graph is exactly equal to 1 of the whole graph, okay? So if you take the measure of the whole space, you take all the area under the graph is 1, and if you take any piece and you take the area under the graph, that gives you the measure of this thing. So this defines a measure on the interval minus 2, 2, and this measure, incredibly, is invariant and ergodic by this map. Okay? So this also means that you know the statistics of all the points, right? Remember, what does Birkhoff's ergodic theorem say? So by Birkhoff's ergodic theorem, mu, so we now have mu, so this mu is ergodic and invariant, as we said, right? Ergodic and invariant. So by Birkhoff's ergodic theorem, mu almost every point, so what is the relation between mu almost every point and Lebesgue almost every point? Here.
Mu almost every point is invariant.
So mu almost every point has a certain property, right? So mu is ergodic and invariant, and by Birkhoff, okay, let me write this a little bit better here. So mu is invariant and ergodic. Okay. So by Birkhoff's ergodic theorem, we have that 1 over n cardinality of I between 0 and n minus 1 of fn of x belongs to A converges to mu of A, right? For all A measurable sets in minus 2, 2. This converges for mu almost every x minus 2, 2. You agree? Remember, this is the corollary of Birkhoff's ergodic theorem that we said. Okay? This means that that I know where all the points, statistically, where all the points spend time, like almost every point. So sorry, there's one more observation to make, which is what is the relation between mu almost every point and Lebesgue almost every point. Therefore, okay, so let me write it as an exercise, but we will discuss it now. Exercise, in particular, this holds for Lebesgue almost every x in this case. Why is that?
Because mu is weaker, like if Lebesgue almost everywhere, so mu almost everywhere.
Why?
Because if every measure is set, if A is a set and the Lebesgue measure is 0, in this case mu also 0.
Exactly.
Lebesgue dominates.
Exactly. So, because mu is absolutely continuous with respect to Lebesgue. You know this notion of absolute continuity? Yeah. Because mu is absolutely continuous with respect to Lebesgue. Okay, remember what does absolutely continuous means? It means that if Lebesgue measure of some set B equals 0, this implies that the mu measure of A is also equal to 0. This is the definition of absolute continuity. Okay, and therefore, what this theorem says is that the set of points that do not satisfy this has 0 mu measure. Okay, and therefore if it's got 0 mu measure, then it must have 0 Lebesgue measure, because if it had if it had positive Lebesgue measure, then it would have positive mu measure. Okay, so the Birkhoff-Sergolnik theorem says the set of points that do not satisfy this property has zero mu measure. Okay, now be careful and claim that if it has zero mu measure, it must have zero Lebesgue measure. Because if it had positive Lebesgue measure, it could. If it's got zero mu measure, it must have zero Lebesgue measure, because wait, which way am I doing it now? I got confused. Lebesgue measure is zero, so if this did not hold for the positive Lebesgue measure set of points, okay, so in this case we have also that Lebesgue measure is absolutely, so maybe we need to use the fact that in this case, oh wait, I'm getting myself confused.
Is the same set A and B, or both of them A?
Oh, sorry. Of course, yes. Yeah. So, wait, let's see if I'm saying the things right. So, we have that there's a set of full measure, so the set of zero measure with this does not hold. Zero mu measure.
This is necessary condition for that. Mu is necessary.
Sorry?
Mu is necessary condition if it's correct.
What necessary condition?
If mu of b equal to 0, then it must be 0.
Right, so if mu of b equal to 0,
Yeah.
then Lebesgue must be 0.
So in other words,
No.
it's not equal to 0, then the first one is not equal.
That's right. That's right. No, that's not what is implied by that. So this says that if mu b no, you're right. So we need to use the we need to use the fact that in fact in this particular case these two measures are equivalent. They're not just, both are absolutely continuous with respect to. Okay, see here, and
Because our function h minus is just modular positive function.
both of them are absolutely continuous with respect to each other. Okay, so in fact we have both. We also have that mu b equals 0 implies the Lebesgue measure of b is equal to 0. Okay, so we have both ways. In this particular case, because of this function here, it goes both ways. And therefore, Birkhoff-Sergolnik theorem says that this convergence holds for mu almost every point, and because these are equivalent, in fact, in this case we use this, the fact that Lebesgue is absolutely continuous with respect to mu, then it implies that this holds for Lebesgue almost every point. So the conclusion of this is that we have a measure that is not Lebesgue measure, that is mu, okay? But this measure controls the asymptotic behavior of Lebesgue almost every point, right? So Lebesgue almost every point visits this interval asymptotically with a frequency that is given by the mu measure of A, not the Lebesgue measure of A. Okay? So if you take an interval of a certain size, of a certain length epsilon, but it's very close to here, then the frequency of visits would be larger than if you take an interval here, right? So when you look at the dynamics of these points, you see that this density is the frequency of visits. So if you plot a histogram, if you use a computer, right, and you take an arbitrary point and you just kind of plot where this point is, you will see that this point will spend more time close to these two boundaries than it spends in the middle. Okay? And asymptotically, the frequency, the asymptotic frequency of the time that it spends here is exactly given by the mu measure of this interval. Okay? That is given by this picture here. You see that this gives you, this area gives you the mu measure, And if you take an interval of the same length here, it will have a smaller mu measure, so almost every point will spend less time close to here than it spends here. Okay, it gives you information about the time it spends in various places. So this is a very powerful, remarkable fact that what we've done, we've started with a map that has no, not much we can say just by looking at this map, by using this push-forward technique and using the very, in some sense, exceptional fact that we have a diffeomorphism that conjugates it to the 10th map, and then we know the 10th map has Lebesgue measures invariant and ergodic. Then we push forward Lebesgue measure, we find an explicit formula for the measure that we know gives you the asymptotic frequency distribution of almost every point. Okay, this is the summary of what we've done so far. Okay, so let's just take a 2-minute break, and then I will give the second example, which is more curious in some sense. So the first example that we've looked at, which is not, we're trying to expand our range of measures that we know, right? From Lebesgue measure and the Dirac delta on fixed or periodic orbits, we now have an example of a measure that is equivalent to Lebesgue measure. It's not Lebesgue measure, but it's absolutely continuous, in fact equivalent to the Lebesgue measure. So that's a very interesting class of measures, okay? And as you see, we proved that in a new class of maps that is full branch, that is not a contraction, it's not an expansion, and it's not a full branch piecewise affine map, right? So it's a new class of maps, and it has this new class of measures. Now we're going to study example 2, and we're going to learn about another class of measures that is not Lebesgue, it's not Dirac delta, and it's not absolutely continuous with respect to Lebesgue. Okay? And we shall see, this gives a very interesting class of measures. So to give an example of these measures, let's consider these two maps. Let me consider here the map 2x mod 1, which we know quite well. So here we know that Lebesgue measures invariant and ergodic. Okay, so we know lots of stuff about this. So Lebesgue measure is invariant and ergodic. So we know we have Birkhoff's ergodic theorem and so on and so forth. Okay, now what about this map, which is also a map from 0, 1 to 0, 1? Let me choose some point P. What do we know about this map here?
Same, is full branch affine.
Sorry?
This is also full branch affine.
Full branch piecewise affine map, yes. So let me call this G. I can, if you want, I can actually give it the exact, I have here the exact formula, but it doesn't really matter. It is, so this is 1 over P to the X, if X is in 0P, and 1 minus 1 minus P to the X minus P1 minus P, otherwise, okay? If X is in P1. Anyway, this is the picture. You don't really need to know the formula in this case, okay? But so what do we know about this? Also Lebesgue measures invariant and ergodic, okay? So what is the difference between these two, Lebesgue measure, invariant and ergodic? And we know that they are conjugate. Remember, this was the key theorem of the first part of the course. Okay? We know there's a topological conjugacy. We do not have an explicit formula for that, but we know. Do you remember how we construct this conjugacy?
Sigma 2 plus z is using
That's right. So we kind of you look at the symbolic coding of the two, right? In particular, if you remember, both of these has a symbolic coding, right? So this has two branches. Let's call it I0 and I1. And this one also. Let's see if I use different. Let me call this I0P because it depends on the point P. And let me just call this I0 and I1. And if you remember, we had this whole symbolic coding of itineraries, right? So every point you code it with zeros and ones, okay? And you can do the same thing here. You code point with zeros and ones here, okay? So everything, this coding is unique except for this, for the boundary point, okay? We discussed how to deal with the boundary points as double coding, but this doesn't really matter. It's only some countable set of pre-images are concerned with this, okay? So what do we conclude about the dynamics? So these are two different maps, but Lebesgue measure is invariant and ergodic for both maps, okay? So this means that if I take an interval here, A, and I take the same interval here, A, almost every point will visit A with a frequency that is the Lebesgue measure of A. And the same thing here. You agree? But remember, the dynamics is different, right? I mean, these are two different maps. If I take this point here, this point, say 1/3 or whatever, with this point here, under one map it goes to one place. If I take the equivalent point here, it goes to a completely different place. These are two completely different maps, okay? But the statistics is the same because in both of them the Lebesgue measure is invariant and ergodic, okay? Now, be very careful here. Let us push forward the Lebesgue measure from here. What do we get? So let us use this conjugacy H. So let mu equals H star of Lebesgue measure. Okay? So Lebesgue measure here, H star lives here. Okay? So mu is invariant and ergodic. For F. So this one I call F. This is F of X equals 2x mod 1 for F. You agree with this? Yes. So what can you tell me about this measure mu? Is it Lebesgue measure? Does this conjugacy map Lebesgue measure to Lebesgue measure? It might, because both of them are invariant and ergodic. I mean, H is certainly not the identity map. Why is H? How do we know that H is not the identity map? What does H? H maps 0 to 0. Where does it map the point P? It maps the point P to 1/2. Right? So if P is not 1/2, then it cannot be the identity map because it maps P to 1/2. Right? H, because of the coding, remember the way it was constructed, it must map this interval I0 to I0, and it must map the interval I1 to I1. Because it maps, this is the crucial point that we're going to use now, it maps points with a certain coding to points with the same coding. if you remember the way it was constructed, if I take a point here that has a coding 0, 1, 1, 1, 0, whatever coding it has, then the image under H will be the other point here that has exactly the same coding. So H preserves symbolic coding of points. Okay? So recall that by construction of H, it maps points to points with the same symbolic coding. So if it maps this interval I0P to I0, it cannot map Lebesgue measure. Well, certainly it maps something that has some small Lebesgue measure to something that has some big Lebesgue measure, so it's not clear. Let's call this mu p. I'm going to put the index p because this all depends, everything depends. Here I fix 1/2, but here everything depends on p. So let me call this mu p is HP. Okay, HP star. Okay, by construction of HP. So you remember the discussion we had about normal numbers, right? So here in the case 2x mod 1,
frequency is one same, but in each parts are same, but in this case is not same.
exactly, right? So what is the frequency of zeros and ones in the symbolic coding? Is 1/2, right? Remember, because if you, this interval is length 1/2, Lebesgue measures invariant and ergodic. So by the formula we wrote before, Lebesgue, almost every point, it visits I0 asymptotically 1/2 of the time. And every time it visits I0, that point will have a 0 in its symbolic coding of zeros and ones. Okay? And similarly, it will visit this 1/2 of the time. So almost every point, if you look at the symbolic coding, which in this case corresponds to the base 2, to the binary representation, okay? But we think of it more dynamically as the symbolic coding, it will have half zeros and half 1, asymptotically. Okay? What about here?
Different P and 1 minus.
1 minus p, exactly, right? So here the same thing, because Lebesgue measures invariant and ergodic, almost every point will visit this interval with frequency the length of this interval, Lebesgue length of this interval, which is p. Okay? And this interval with length 1 minus p. Which means, what is the symbolic coding of almost every point here? It means that if you look at almost every point, and you look at their symbolic coding, the digit 0 will occur asymptotically with frequency p. And the digit 1 will occur asymptotically with frequency 1 minus p for almost every point. How can we explain this? How is that possible? That in one case, you get that almost every point has asymptotically, half the digits in the symbolic coding is 0 and half is 1. And here for Lebesgue, almost every point in the asymptotic frequency, the symbol 0 occurs with frequency p and 1 with frequency 1 minus p. Is there a problem? Is there a contradiction there? Is there an issue or not? No, it's okay. So here we have a set. Shall I write this down? So there exists. So let A, let me write it like this. Let AP Okay, let me use the notation that I have in the notes. So let A P equals, so let me call these two intervals here. So this is 0, 1. So just to distinguish, they're both intervals 0, 1, but here let me call this IP equal to 0, 1, and here we'll just call it I equal to 0, 1, right? So we know which map we are working with. So AP is a set in here. AP is equal to all this set of points X and I, okay, which have symbolic coding such that the symbolic coding of X contains asymptotic frequency P of zeros, and the same thing for, let me call this APP is equal to X in IP, okay, with the same property. Okay, so here, this set is that the Lebesgue measure of APP is equal to, sorry, the Lebesgue measure, I'm using Lebesgue measure. Lebesgue measure of APP, in other words here, the set of points whose asymptotic proportion of zeros is P, is almost every point has this property, right? So the Lebesgue measure is equal to 1. Okay? But here, Lebesgue measure of AP for this map, this is with respect to F, right? And here is with respect to G, right? Because we're looking at different spaces and different maps, of course, okay? So the symbolic coding is always with respect to a particular dynamics, a particular partition, so that's where we have the symbolic coding, okay? So what is the Lebesgue measure of AP, which means here in this map under F, we look at all the points with the symbolic coding of 0 is the frequency is exactly P. What is the Lebesgue measure of this set of points? If P is not 1/2, then this Lebesgue measure will be 0. 0, okay? If P is different from 1/2, because we know that almost every point, the asymptotic frequency of zeros is 1/2 for this map. Takes a little bit of time to digest. So maybe there's a useful observation to be made here, that if you remember, here you can find every possible sequence of zeros and ones occurs. Remember when we did the symbolic coding of this, you can get every possible sequence of zeros and ones. Okay? So, in particular, of course, you can get some points where the asymptotic frequency of zeros is 1/2, in fact, for almost every point, but you can also get another point where the asymptotic frequency of zeros is 1/3, or 1/4, or P, whatever. Okay, there's a very rich set of points. So this set of points has 0 Lebesgue measure in here, but it's still a huge amount of points which have all kinds of possible symbolic coding with all kinds of possible frequencies. You get points where the frequency of zeros does not converge, right? We have points where the frequency of zeros may be large and then it becomes small and so on, or you may have points where the frequency of zeros converges to any given number. You give me a number between 0 and 1, and I construct a point which has the symbolic coding where the frequency of zeros is exactly that number. Okay, every number occurs. Okay, it's just that in this particular case, all the set of those numbers that do not exactly have the frequency of zeros is equal to 1/2, the union of all of those has 0 Lebesgue measure. Okay, incredibly, even though you can have all this possible behavior happening, Lebesgue almost every point has just one type of asymptotic behavior, which is that the asymptotic frequency of zeros is exactly 1/2, and the asymptotic frequency of one section. Okay? So what seemed like an obvious thing when we first did it in terms of the, where the frequency of digits is exactly 1/2, but you need to put it into context to remember that all the other possible cases also happen. Okay? So it's quite remarkable that Lebesgue almost every point just chooses this exact one behavior. So where does this measure live? Okay, so I'm giving you now the background that we need to understand what our question is. Our question is, we have done the push forward. Okay, we're looking at this measure here.
Our measure using we can estimate a movement below if the big measure in this set in this dynamic and over 2 pi and the big measure over 2 1 minus pi.
Well, let me be a little bit more drastic here, right? So, how about the following? So, how about we measure mu p of AP?
This is the
AP is here. Mu p lives in this space here, right? Because we have pushed forward Lebesgue measure. Here we have Lebesgue measure, and we push it forward here. Okay, mu p lives here. And this set also lives here. Okay, this is the set of points x in I, whose symbolic coding contains frequency p of zeros. Okay, I've just defined this set. So what is mu p of AP? Well, by definition, this is equal to HP star of Lebesgue of AP. Okay, and this is equal to Lebesgue of HP minus 1 of AP. Okay? Now what is HP minus 1 of AP? Remember, H is this conjugacy, okay? And H maps preserves the combinatorics. In other words, H preserves the symbolic coding. Okay? So any point here, X, maps to another point which has exactly the same sequence of the symbolic coding. Okay? So this means that these two sets, they're defined in terms of their symbolic coding. Okay? So if you have a point that has a symbolic coding that contains asymptotic frequency P of zeros, then its image, its pre-image under H, will have exactly the same property, right? Because the asymptotic frequency of zeros just depends on the sequence that defines the symbolic coding. Yes? So this will be exactly the Lebesgue measure of APP. Right? Because these are the points here that have exactly the same asymptotic frequency. Okay? So H, the map H, maps at least the Lebesgue measure of these points is exactly the same as the Lebesgue measure of these points, because all the points, this set is exactly the same as this set. Okay? Because, and this is equal to 1. Exactly. But what is the Lebesgue measure of AP? Okay, so mu p of AP is equal to 1, but the Lebesgue measure of AP is equal to 0. Nothing strange with that. Takes this a set of points AP. Okay, I look at these points here. I look at all the points whose asymptotic frequency of P is 0. Okay, now this set, is this set invariant set by the dynamics? It's invariant. Is it forward and backward invariant? It's forward and backward invariant, right? Because if you take any point in here, its image will also be in here, its pre-image will also be in here, because this characteristic is defined based on the asymptotic frequency of the sequence, right? So if you take any pre-image, it will always hold this. So this set here is forward and backward invariant. It's a fully invariant subset of the interval 0, 1. Okay, so we can think of the dynamics restricted to this subset, right? This is a subset that is fully invariant. Remember, so any point that is in this subset, any image or pre-image belongs to this subset. Okay, and this measure lives on this subset. This measure gives measure 1 to this set, and therefore gives measure 0 to the complement of this set, to everything else. Okay, and this set has 0 Lebesgue measure. Why does it have 0 Lebesgue measure?
Because P doesn't equal to 1.
Exactly, because we know that almost every point for this map has exactly 1/2 frequency of zeros. How many points belong to this set? Just from, again, from a topological, symbolic point of view. Is this a countable, uncountable set? It's an uncountable set. It's a big set of points. Okay? I mean, in fact, in some sense, topologically, it's the same as saying if P is a half, then we get all the points with a asymptotic frequency of zeros is 1/2, or P, what's the difference? I mean, you're taking all the set of points that have a certain fixed asymptotic frequency of zeros. The fact that we choose 1/2 or some other point P, from the point of view of the set of all sequences, it doesn't make any difference, right? It's just, in the set of all sequences, there exist uncountable points whose frequency of zeros is 1/2, uncountable points whose frequency of digits is any given number. Okay, so it's the union, the set of all possible sequences is the union of all the sequences whose asymptotic frequency of zeros is any number between 0 and 1, right? Plus lots of other points where the asymptotic frequency is not well defined because it does not converge. Okay, but certainly it is the disjoint union of all the different, if you take another P prime, then AP and AP prime would be disjoint. Is that clear? Because you fix the asymptotic frequency P of zeros. If you take another point whose symbolic coding has a different frequency, the points cannot belong to both, right? Either they belong to one or they belong to the other because you fixed it. Okay? So the whole interval is the union. Let me see if I can now kind of summarize what we've been saying and conclude what we want to conclude. So notice that let's make these remarks. Notice that let's write here that AP F minus 1 of AP is equal to AP, right, is equal to F of AP. So each of these APs are forward and backward invariant, okay, which means we can talk about the dynamics restricted to each AP. And 2 is that they are pairwise disjoint, right? So if P is different from P tilde, okay, implies that AP intersection AP tilde is empty, the disjoint, pairwise disjoint, okay? And of course, okay, this is a kind of trivial statement, but the interval 0, 1 contains, obviously, the union for all P in 0, 1 of AP. So you actually have an uncountable family of pairwise disjoint sets, each of which is uncountable. Is that clear? Okay, and there's lots of other points besides, because there's all the points, these are all the points where the frequency of zeros and therefore the frequency of ones actually converges to something specific. But there's lots of points where this frequency does not converge. Yeah? Because when I say here the asymptotic frequency, you understand what I mean, the asymptotic frequency. I will put this formula. So you look at the first 1 million digits and you count how many zeros there are, and then you take this proportion, you look at the limit and you see if it converges. So there's many points in which it does not converge. Okay, and what have we just constructed? And there exist, so there exists measure, there exists family mu p, p in 0, 1. Well, actually the cases 0 and 1 are kind of trivial, so let's put it in the open interval 0, 1, okay? Invariant ergodic probability measures. Such that mu p of AP is equal to 1. Agree? This is what we just showed. Okay, for each p, we do this conjugacy, and we define mu p to be the push forward of Lebesgue by the conjugacy that maps that particular map, GP to F. And okay, this is it. So this means that in particular, if P is different from P tilde, then mu P and mu P tilde, we say that they are mutually singular. Have you heard this? Each one is a singular measure with respect to the other. Okay? This means that there exists a set such that one of them has full measure on the set as the other one has zero measure on that set. Okay? Because each one of these gives full measure to AP, but all the others, they give zero measure to AP. Because all the others, they give full measure to the other, to their own. Each mu P gives full measure to its own AP. Right? So they all live on different sets. Okay? They're all mutually singular. So this is what I said when I said we will introduce another class of measures. Okay? So we have seen Lebesgue measure. We have seen the Dirac delta on fixed points or periodic points. These are the two simplest and most basic examples. Then in the first part of the lecture we saw a measure that is not Lebesgue measure but equivalent to Lebesgue measure. Right? And now we see a very interesting class of measures which are singular with respect to Lebesgue measure, but they're not Dirac delta on fixed points. They do not give positive measure to any single point. Right? These are non-atomic measures, so they do not. They are on this set. This is an uncountable set, and these measures they do not. There's no single point that has positive measure. Right? That's the different. So Dirac delta measures are atomic measures because there exists a single point that has positive mass. Whereas this one, there's no single point. Every single point still has zero measure, but it's really this uncountable set on which this measure lives. Okay? And on this uncountable set, you have all these dynamics. So all of these measures, they exist for the map 2x mod 1. Okay? Simultaneously. Remember, the way we constructed them is with this conjugacy. But really what we're saying is that if you take, and I will finish here, if you take the map 2x mod 1, okay, you say, okay, what is the space of all invariant ergodic measures for this map? Okay, so the space of all ergodic invariant probability measures includes Lebesgue measure. It includes all the Dirac delta on all the periodic points, which is already a lot of measures. Okay, it's a countable set, but it's all distributed. So Dirac measures on periodic orbits. And it includes these measures mu p, okay, defined above. All this family of measures for any p, and they're all coexisting all at the same time. Okay, here. So this is what we mean by the fact that there's a very rich dynamics and coexisting a lot of different measures, different invariant ergodic measures. So we'll discuss next time, given that there's so many measures, which one do we prefer? There are so many invariant ergodic measures to choose from, okay? In some sense, you know, when you're given a dynamical system, how do you decide which one you like, or how do you decide which one? I mean, in some sense, we just want to study all the possibilities, but are there some that are more important than others, for example? Are there some that we're more interested in? Okay, we will discuss this a little bit. Any questions? Okay.